Bad idea.
Here comes it like a third of our class.
You want to make this into a competition?
I do.
Did you get a haircut?
Yeah.
Looks good, man.
We can make some better death parade.
Yeah.
Wait, Zach, did you get a haircut?
That's easy.
Everybody
got a haircut.
I'm getting my hair cut Wednesday.
I'm thinking about getting like
What?
this cut.
I feel like we do the exact
over
same
the
thing.
break.
Like, you look somewhat like,
You probably use some sort of
like,
concentrated microwaves.
oh, what's his name?
What's on his budget?
The guy who played in National
time
Treasure.
though.
Yes.
Oh,
I'm the only one who
okay,
sees that.
Exploding galaxies.
It's not just when I'm thinking.
Exploding galaxies.
It's not just when I'm thinking.
Exploding galaxies.
Okay.
You should
I'm not allowed to.
Maybe it is.
Galaxy.
Oh, you're gonna harvest that energy.
Yeah.
You're just gonna suck up that energy into
Oh, no,
crystals.
he's half the pieces. Like there's a tiny chance that the galaxy explodes at you right enough. That's why you have to wait to really like.
Oh yeah.
Okay.
What part of rock are you gonna be in?
The best choice.
I honestly don't know.
Of art, yeah.
I just know how to get to my class.
Okay.
Okay. So we're beginning Chapter 8, Study of Gravity, and at this point I decided for your first assignment to introduce polar coordinates, which we will use extensively next semester. And it's kind of interesting to see them here because polar coordinates make a nice way to describe uniform circular motion, which is one possible solution for a planet going around the sun. So it makes an interesting time to introduce you to polar coordinates. We're going to need them a lot next term. So let's go over what happened here. There we go. Try that again. It's still kind of weird. Oh, I see. How did that get over there? All right. So we're going to be developing a different way of tracking either points in a plane or also vectors, vector fields. So we'll begin by just considering the coordinate system. So the Cartesian coordinate system that you're familiar with takes two orthogonal directions, x and y, x hat, y hat, and assigns to a point a pair of numbers, which can be used then to describe the vector r from the origin in terms of expression like that. Move so many units along the x direction, so many units along the y direction, and that's then the net displacement from the origin. Okay, so the vector in that case is described in terms of two orthogonal directions. So now in polar coordinates we're going to do something different. I'm going to rewrite this arrow here. In polar coordinates we're going to describe the same vector, but in terms of, rather than x and y components, two other numbers, which are the distance and an angle, relative to horizontal, relative to the x-axis. So then rather than specifying go x along the x direction and y along the y direction, we actually pick out the direction by specifying an angle theta. So theta gives us a direction, which is going to be called r hat. So r hat is a unit vector in the direction of r, and its direction is specified by theta. And the usual convention is that theta here in this context is measured counterclockwise with respect to the x-axis. So pi over 2 is horizontal. So if that direction is specified, then I could write this vector r as a combination of a distance and a direction. R hat specifies the direction, and r hat is specified by the angle theta. And the magnitude is just r. makes a much more compact, simpler way of describing a vector. Give me the direction in terms of an angle and give me the distance r. Okay, well, we can relate this back to what we had before. And we can discern, as you did in your homework, a relationship between r and r hat and x hat and y hat using trig. And one of them, of course, is that the distance is the sum of the squares of the displacements in the x and y direction. And that the tangent of the angle is the ratio of y over x. And that I could also reverse this if I have, in other words, this specifies how to find r and theta from knowing x and y. And in the reverse direction, if I know r and theta, find x and y. Just the usual trig relations, like this. So I can go back and forth in terms of the coordinates. In the same way, I can establish the relationship between the unit vectors, the r hat, then in terms of x hat and y hat. So I could, in your homework, you should have discovered that r hat is simply a combination of two directions, x hat and y hat, like that, using the trig relation. Okay. R hat is a unit vector, and its direction is established by theta. Now, we want more than one unit vector, though. In order to be able to describe things generally, we need two directions in a two-dimensional plane. And r hat, then, if this is r vector, the r hat points along that vector away from the origin. And so no matter where this point is, no matter the value of theta, r hat is pointing away from the origin along the direction theta. Let me clean this up a little bit here. Okay, so this is then r hat. Okay, but I need a second direction. So r hat is in the direction of increasing r. If I think of this point here as being specified by a combination of r and theta, that is distance and direction. So r hat is in the direction of increasing r. Just like x hat was in the direction of increasing x, y hat is in the direction of increasing y. So that suggests another vector, which would be using the other coordinate, theta. Let's choose a vector which is in the direction of increasing theta. So if I look at this point here, and if I determine how it moves, for example, if I want to increase r, well, it's obviously in the direction of that red arrow. But if I want to have a vector which is in the direction of increasing theta, it would be this way. I'm going to call that theta hat. It's going to be perpendicular to r hat. And it's the direction that I move in if I increase theta while holding r fixed. Okay, now, from that, and again some trig relations, you should actually be able to demonstrate that theta hat is going to be, minus x hat sine theta plus y hat cosine theta. This you can get simply because it must be perpendicular to r hat. But there's another relation which will be helpful to establish here. And I'll give you the motivation for that. We can understand that there's a relationship between r hat and between theta hat in the following way. Let's go back to this point here. Here we have r hat is in this direction for a given value of theta. Now let's increase theta by some amount, keeping r fixed. So the arc length is held fixed, r, and we increase theta by a certain amount, delta theta. And then, so this is r hat of theta. Now this points to a slightly different direction. In fact, I over-exaggerated there. A slightly different direction, r hat of theta plus delta theta. And I want to take the difference between those two unit vectors. How does the unit vector r change if I increase theta? well, it can't change in magnitude. All it can do is change in direction. And so if I compare r hat to r hat plus delta, to r hat of theta to r hat of theta plus delta theta, I take the difference between them, and that's this vector here. And that's going to be then, as delta theta gets smaller, that vector is going to be perpendicular to the original r hat. And so that's going to become proportional to our theta hat. That gives you an idea of why theta hat up here is perpendicular to r hat. So in other words, what I'm establishing here is that theta hat is the derivative of r hat with respect to theta. Remember, r hat is a function of theta, and so is theta hat. They're both functions of the angle, which you can verify going back to our expression for r hat, then taking the derivative of this with respect to theta. In fact, that does give us minus x hat sine theta plus y hat cosine theta. So you should be able to verify these relations. R hat is in fact a unit vector. Theta hat is also a unit vector. And r hat dot theta hat is 0, which means that they are perpendicular. Okay, so that gives us the beginning of a coordinate system. Then we're going to express everything in terms of r and theta and r hat and theta hat. So before, where we had x and y and x hat, y hat to describe a vector, for example, the position, now we're going to use coordinates r and theta and the direction vectors r hat and theta hat. Okay, so let's study how this comes out then when we're dealing with uniform circular motion. So we begin by, and oh, by the way, I should notice here, I just noticed on my way over, in the solution, where it gets to be handwritten part, I made a change in notation that didn't make it to this solution sheet. So please read in the solution sheet where it says rho, please read r, and rho hat should be r hat, and then everything will be consistent with the text and the other solution sheet. I'm going to fix this and get it back to you, but that's so you can read the solution here. There are different different choices of labels for these coordinates, and my old solution had rho instead of r. Okay, so.
Use phi.
And phi, thank you. Phi instead of theta, yes, thank you. So phi goes to theta, and phi hat goes to theta hat. Thank you very much. I didn't even notice that. Okay, makes it a little harder to follow. Sorry about that. I'll fix that, but you should be able to decipher it. Okay, so let's go through this uniform circular motion. So what characterizes uniform circular motion? There's two characteristics.
Constant velocity.
Constant speed.
Or speed.
Constant speed, right? Not constant velocity, because the direction is changing. So constant speed and constant
acceleration and phasing.
the magnitude of the constant acceleration. But I was thinking actually it's circular motion. So what characterizes, why is it called circular? Because the distance from the origin is constant, right? And what makes it uniform is that the speed is the same all the way around. So those are the two things I was looking for. So r is a constant, and theta is increasing linearly in time. So this is what characterizes uniform circular motion. So it's tooling around the circle, and the angle is just increasing linearly with time. So it's it's uniform rotation, analogous to uniform translation. All right, so now let's see if we can work out how this position vector is going to look for uniform circular motion. The position vector as a function of time, but I want to do it in polar coordinates. So the distance is r, which is a constant, and then the direction is r hat, which depends on theta, where I'm going to use this relation that theta is proportional to time. So theta dot is equal to omega, and theta double dot is equal to 0 because omega is a constant. In other words, it has constant angular velocity, so there is no angular acceleration. Okay, so then let's, as the solution shows, the plot of r and theta are quite simple. Now let's take the derivative of the velocity with respect. Let's take the derivative of the position with respect to time to get to velocity. Now, in principle, I should be taking the derivative of everything here. So I have two terms to begin with, because I've got a multiplication of the r and r hat. But that first term, the derivative of r with respect to t is what? 0, because r is a constant. R dot for uniform circular motion. R dot is 0. And now we have this dr hat dt. Okay, and we can understand that because theta is a function of time and r hat is a function of theta. So we're looking for dr hat of theta of t. So we're going to apply the chain rule. So this is dr hat d theta times d theta dt. And dr hat d theta we established was theta hat. And d theta dt is theta dot, which is omega, constant. Okay. So that says then, having worked this out, then the velocity is equal to r omega theta hat. Right? We have a factor of r from here, and we have a factor of omega from here, and so that gets us the velocity. So notice that the velocity is in the direction of theta hat. And if we go back to our diagram explaining where we set up theta hat, you see that the velocity is in that direction, theta hat. So it's where the radius vector is pointing radially outward. Theta hat is tangent to the circle. So the velocity then is going to be tangent to the circle. So if we have here is r hat, the position vector is going to be r hat, so this is direction r hat, and the distance is r. Now the velocity is going to be perpendicular to that. The velocity is going to be along theta hat. Theta hat is in this direction. And the magnitude of the velocity, as you can see from this, is just going to be r omega, because theta hat has magnitude 1. So the speed is r omega. Okay, now we've confirmed then r is a constant and omega is a constant, so the speed is a constant, which is what we wanted to have for uniform circular motion, that the speed was a constant. The velocity is changing direction as this thing moves around. Notice what these unit vectors are doing then. As this particle moves, suppose it gets over here, theta is now bigger. The magnitude distance from the origin is the same, but now r hat has shifted. R hat is over this way, and theta hat is this way. Notice then that these unit vectors are changing as the particle moves around its circle. The unit vectors are following it. And that might seem at first to make it more complicated, not simpler. The nice thing about Cartesian coordinates is they simply don't change. And so when you take derivatives with respect to time, x hat is not, it doesn't change, so the derivative of x hat with respect to time is 0. So you never have to deal with the derivatives of the unit vectors. Well, now these unit vectors are changing in a way that depends on how the particle is moving, because it depends on how theta is changing in time. And at first you might think, wow, this is going to be more complicated, but it turns out actually to be simpler if you go through this initial math at the beginning. Once you work it out in a consistent way in terms of polar coordinates, it actually turns out to be simpler, especially for uniform circular motion. Okay, so now let's go to the next step. Let's do the acceleration then. So we have the velocity vector. Now let's take the acceleration as the derivative of the velocity vector with respect to time. And the velocity vector was r omega theta hat. And r and omega are constants. So I'm not going to bother to write down that their derivatives are 0, right? Remember that r and omega are constant. So now we need the derivative of theta hat with respect to time. Okay, so we had theta hat was minus x hat sine theta plus y hat cosine theta. Let's take the derivative of theta hat with respect to theta. Okay, and then we get this combination So what is that derivative there, d theta hat d theta? Look at that expression inside the parentheses. Anybody recognize that? It's r hat. So we have this is minus r hat. So we have this interesting pairing. Dr hat d theta is theta hat. D theta hat d theta hat d theta is minus r hat. And then you can look at, again, if you go back to that understanding that we were doing with the derivative of the r hat, do the same thing with theta hat. Theta hat's turning towards the center. Here's theta hat here. And then at a later time, or bigger angle, theta hat is shifted. And it's rotating towards the center. It's rotating towards the middle. And that's why we have this relationship here. D theta hat d theta is minus r hat because theta hat's having to turn towards the center of the circle, which is, in other words, in along r hat. Okay, so now we can use the chain rules again. So we had up here, we had d theta hat dt. Well, remembering that theta hat is a function of theta. And d theta dt is, again, omega. D theta hat d theta is negative r hat. So that gives us d theta hat dt is minus omega r hat. So the acceleration in uniform circular motion is minus r omega squared r hat. And the magnitude of that is r omega squared. So let's summarize here the magnitude of the speed and the accelerations. The magnitudes are given by this. So if we know r and omega, we can find the speed and the acceleration, and the directions are what we've indicated there. And some people will write this as the acceleration is v squared over r, which is another way of eliminating omega but keeping the speed and the distance. So the acceleration required to keep a body moving in uniform circular motion at a circle of radius r, speed v, is v squared over r. Now, what should supply that? Well, that depends on the circumstance. If this is something being swung around a circle on the end of a rope, then the tension in the rope is providing that force that would give you that acceleration. So then you could find, suppose we have something on the end of a rope, and it's moving with speed v in this direction, moving in uniformly around the circle, radius r, and this body has mass m. The tension in the rope, which would be the only force acting on this body in this situation, the tension must be mv squared over r. Right? So that tells you then what the tension in the rope must be in order to keep that thing moving in a circle. If this were a car moving around a racetrack, circular racetrack, then what would provide that force?
Friction in the tires.
Friction in the tires would provide that force. It would have to be of the same magnitude, mv squared over r. If this were a planet going around the sun, which is coming up here in this chapter, if this were a planet going around the sun, the force of gravity would have to provide that, and the magnitude of that force would have to be mv squared over r. So you see, no matter what the circumstance is, you can tell what the magnitude of the force is as long as you know the speed, the mass, and the radius of the circle, uniform circular motion. Okay. Now, the second part here of the homework, you're to get it. This is a little bit more complicated. Let's get away from uniform circular motion. Let's suppose that we have two coordinates, r and theta, which are themselves functions of time. And you need to work out the derivative. So it's like we did before, where x was a function of time and y was a function of time. And then to get the velocity and the acceleration, we take the derivatives. But those are really simple because x hat and y hat are not themselves functions of anything. They don't change. So the velocity was just x dot x hat plus y dot y hat. And the acceleration is just x double dot y hat plus y double dot y hat. Well, it's not going to be so simple when we're dealing with polar coordinates because the vectors, the unit vectors are themselves changing. And so you have all those chain rules that I showed you. So I'm going to leave the details for you to go through the homework. But the velocity is r dot r hat plus r theta dot theta hat. That gives the velocity. Notice there are two components of the velocity. There's a component along the r hat direction, and there's a component along the theta hat direction. In uniform circular motion, that first component vanished. There was no velocity along the radial direction. That's because the distance never changed. Okay, and you get this simply by using the chain rule as we did earlier. Come up here. Here's the velocity, okay? And instead of getting rid of that first term, you keep that first term, that dr dt, we said was 0 in uniform circular motion. While in general, it's not 0. So that would be r dot r hat, and then the next term gives an r omega times theta hat. Okay? So you can see how to go. What we did is just one extra step here. It's keeping in mind that the r dot does not vanish, and that theta dot is not in general a constant either. And then the next derivative, a. So I'm going to write down the results here. The details are in the homework. It's a little complicated. Okay, in uniform circular motion, the acceleration is entirely back in along the radius vector. But in general, you have acceleration along the theta direction, just like you have velocity in general. It's along the radial direction. So it's a complicated looking expression. It doesn't look like we saved ourselves a lot of work here. But it actually is going to be simpler for a lot of cases, especially when you get to studying planetary motion, as we're just about to do. So these are the components. These are the radial components. The radial component of the velocity, the radial component of the acceleration. And these are the angular components. I should put that green. Angular components. Angular component of the velocity, angular component of the acceleration. So that's the general expression for velocity and acceleration if I know r and theta as functions of time. It's a general expression, so I should draw a line here. This is now in general. So that's the polar expression. You can see that corresponds to what we got in Cartesian components, where we have x dot, y dot, x double dot, y double dot. So this is the corresponding expression in polar coordinates. Okay. So let's go and look at now the problem of gravity. So are there any questions about polar coordinates before we move on to gravity? We're going to use polar coordinates a great deal. For example, we're going to consider a wire carrying current, produces a magnetic field around it, and we're going to use then polar coordinates to describe the magnetic field produced around a long wire. Because if you take a cross-section of it, the natural system of description is a polar system, just like what we've got here. So that's the next step. We haven't done this, is to describe fields in general in terms of these coordinates, and that's what we haven't done yet, but this is the first step to getting there. So we're going to use the polar coordinate system quite a bit next term. So it's good for you to become familiar with it. All right, so now I wanted to use this principal result. That is the velocity, the acceleration for uniform circular motion is v squared over r. Now we got this actually a different way previously. We got it using just strictly Cartesian components when we were doing at the beginning of the chapter on rotation. We did this problem. We also got it now using polar coordinates, so we got it more than one way. All right, so the force then is going to have to be of this magnitude. In order to keep something moving in a circle, speed v, uniform circular motion, speed v, radius r, mass m, body moving in that, it's going to have to provide a force of that magnitude. Okay. All right, so let's take a step back historically. Both of the combination that happened historically that Newton accomplished, both of these. First, there was his general description of motion in terms of momentum and force, which we now have a better understanding of in terms of impetus as the cause of locomotion, and then force as a change of a way of changing the momentum, changing the impetus. And momentum is the measure of the impetus. Okay. So that constitutes one way of describing motion, and that's what we've been doing all term. We've done uniform linear translation, uniform linear acceleration. We've done simple harmonic oscillator. We've done uniform rotational motion, uniform rotational acceleration. We've done all these different aspects of motion. We've demonstrated that motion is independent in different independent directions, so we could have acceleration in one direction and uniform translation in another direction. All of this was possible in this empiriometric way because of Newton's laws, right? Newton's three laws, the development of calculus to go along with it. Okay, so, and let's recall the forces that were involved. So in that we had forces, and we had lots of different kinds of forces. So what were some of the forces that we had? Let's make a catalog. Tension in a rope, which was established because the rope was stretchless, and it was then whatever force was required to keep the rope from changing length, right? What else? Friction. We had two kinds of friction, static and kinetic. Static, again, was of such magnitude as to resist slipping, and kinetic was always to try to bring slipping to an end. The magnitude of kinetic friction was determined as proportional to the normal force. The static force was determined by circumstance, but it didn't have an upper limit. Okay, but this represents the first clear case of what I'm going to be establishing here in a minute. So tension and static friction are kind of circumstantial forces, or whatever is necessary to keep a body from stretching the rope or from sliding. Other forces. Gravity. Pardon? Normal force. Good, thank you. Normal force. Okay, so the normal force, what's the magnitude of the normal force? Again, circumstance. Whatever the circumstance is, it's whatever force is required to keep it from falling through the table, right? So I'm going to outline here in green the circumstantial forces. That is ones that depend, whose magnitude depends on the circumstance, and you often have to solve the problem in order to be able to determine the magnitude of these forces. What is the normal force, static, friction, or yes, sir?
If the normal is circumstantial, wouldn't that make kinetic circumstantial too?
In that case, yes, right. Okay, yeah, you could say it's secondarily circumstantial. Yeah. But it's often easy to determine the normal force within one step. But you're right. Thank you. Other forces. What else do we have? Do we have any others? We did.
We haven't really used air resistance, but
Yeah, we did very briefly. We talked about air resistance, so I'm going to put it on here. And and this one, the magnitude of the force is proportional to the velocity. That was our idealization of air resistance. Okay, and so that falls under the category of the red ones that I'm going to be drawing up here. Oh, gravity. What is the magnitude of gravity? Well, near the surface of the Earth, it's just mg. Okay, so The ones that I'm circling in red, I have a well-identified force law. There's another one we're missing.
The spring.
Spring. Yep, that's the one I wanted. Thank you. The force law is minus kx. So this force, the magnitude of the force exerted by a spring is just proportional to the stretch of the spring. Okay, so for those cases where I can write down a force law, then the problem becomes simply one of solving the differential equation. That is, I have a force law, for example, for the spring, mx double dot is minus kx. And then it becomes a matter of solving the differential equation. Or, for gravity, my double dot is minus mg. Even easier because the right-hand side is a constant. Right? In that first example, x is a function of time. So, in other words, what we get to using Newton's second law combined with a force law gives us then, converts it all into a matter of mathematics. I get a differential equation that I need to solve. So this is the general strategy then. I have to have, I can start with Newton's second law. If I can write down something, the description of the force law, then that completes the picture, and then I'm just looking for a mathematical problem solving, and I can turn the crank. All right, so that sets the stage then. The laws of motion came first, and he's playing around with this, trying to solve different situations. And I'm trying to remember who it was that was it Halley? I think it might have been Halley. Was having a conversation with Newton about planetary motion and these things that Kepler and let me back up a little bit. You maybe know some of the story about Tycho having made observations of the positions of planets in the sky, very careful measurements, really not that could have been done sooner. They could have been done quite a bit before that. Nobody apparently took quite the care that Tycho did. Didn't require any particularly advanced technology, but he very carefully measured the positions of planets in the sky over months and years. Kepler took all of this data and tried to make sense out of it in terms of understanding how the planets were moving in the sky, because there was some still debate about how are the planets moving? Are they going around the sun? Are they going around the Earth? Exactly how are they moving? Of course, there were these two systems. The Ptolemaic system had planets going in epicycles. So if you watch planets in the sky, if you do something like this, the planets that are closer to we know now are closer to the sun, Mercury and Venus, have very simple motion. They don't get ever very high above the horizon. You see them at sunset, sunrise. That's about it. But if you look at a planet like Mars, it will move through the sky in a certain. It'll go this way, then back, and then go like this again. Or maybe I've got it backwards. It's going this way, then back, and this way. Okay. Very odd that there should be this not steady motion. And many people speculated that was because the Earth was on the inside track, so to speak, and could, as it approached Mars, it appears that Mars is actually moving in retrograde motion because the Earth is passing it. So he was able to determine that, in fact, this was completely consistent with Tycho's data. In fact, to the point, it was precise enough that he could determine that the orbits of the planets around the sun were not, in fact, he could determine that they were ellipses, with the sun at one focus of the ellipse. And this is when we're talking about ellipses that are not really very eccentric, like Mars's orbit is not particularly eccentric. It's almost a circle. And the Earth's orbit is almost circular as well. So they were very good measurements. Okay, but he made some also an observation that seemed to be that the so I got to get this right. The which one is that?
It's the R cubed one, right?
That's right. The period of the orbit is proportional to the cube of the radius if we're talking about circular orbits. If we're talking about elliptical orbits, it's actually the semi-major axis and not the semi-minor axis. Kind of an odd thing. It's this distance and not the one going across. Not that one, but the long one. which he got from having a handful of these planetary orbits that he could observe, not many of them. So this is one of Kepler's observations, which also might appear to hold for certain comets, like Halley's comet. So I think it was Halley who was having a conversation with Newton, and Newton said, "Oh yeah, I figured all that out." And it was like, "You did? You understand all of this?" And he said, "Oh yeah, I figured that out. I should write that up." And so Halley said, "Well, yeah, you should." So that was I'm paraphrasing. I think the conversation wasn't quite like that, but it was encouraging him to, I'd like to see that. A lot of people would like to see that. So that was the motivation for writing down the Principia Mathematica, where he started writing down all of this stuff, including so the force law for gravity then that he determined was necessary was that the force of gravity was proportional to the masses of the two bodies and inversely proportional to the square of the distance between the two bodies. Okay, so now actually you can see Kepler's third law, I think it is, falls out of this very neatly. So let's look at this. Let's suppose that then the force of gravity, the force law, this is the F, and then I need the ma, which is supposing that the planet goes in a circular orbit around the sun, the mass of the planet over the velocity squared divided by mv squared over r. Let's see. Yeah. So if I write that in terms of omega squared, that's what I should do. Remember, the acceleration was r omega squared, because I want to write it in terms of the period of the motion, and it's easier to get the period using omega. Okay, notice that the mass of the planet drops out, and Kepler's third law was independent of the planet, the relationship there. So this is equal to then r cubed, and omega, remember, is 2 pi over the period, so that's squared. So in other words, t squared goes like r cubed. Comes straight out of the combination of the force required to keep a body moving in uniform circular motion and the inverse square law for the gravity. Just drops right out, right? It's just amazing how simple. Now, what is harder to prove is that when the orbit is not circular but rather elliptical, that what you should be using is the semi-major axis and not something else. Why has it come out that semi-major axis, and how in the world Kepler figured that out, I don't know. But in any case, it turns out that if you can actually, what Newton did was to prove in general that the orbits under an inverse square law are in fact ellipses like this, or circles being a special case of an ellipse. In other words, he explained Kepler's observations that the planets seem to be moving in elliptical orbits and have this relationship between the size of the orbit and the period of the motion. It was all there. So this was it. This was the beginning of modern science. This was the first fully empiriometric theory that combined a fully quantitative description of motion along with a force law in a tight mathematical form. So we're not going to go through the derivation of that step. In other words, proving what I just said, that planets move in circular orbits in an inverse square law. You'll do that when you're juniors. Okay? We're not going to do that here. So I'm just going to tell you that the resulting equations of motion give us elliptical orbits, and we're not going to prove that. So in other words, what we've got is, I want to start with Newton's law. Let's see, that's the planet there, over r squared, and I want to have an r hat here for direction using polar coordinates. So I want to solve this, and this is what gives you elliptical orbits. Not going to do that this year. I'm going to wait a couple of years for your math muscles to get a little stronger, so you can understand the steps required to get the solution in this case. But it makes use of polar coordinates, and the tantalizing result that you can get within just a couple of steps here. The t squared goes like r cubed. It's very easy to get for uniform circular motion. Okay, so now this is a big step then, this inverse square law. And how does he come up with that? And why is it that, for example, here on the surface of the Earth, it appears that the force of gravity doesn't seem to change very much. Go from one place to the other, go from here to here, and the force of gravity doesn't change much. Well, that's simply because r is pretty big compared to this distance, and so there isn't much difference. And 1 over r squared doesn't change much if I add 10 feet to it. When r is hundreds of miles, thousands of miles, then it's adding 10 feet doesn't make much difference. Mr. Kelly, do you have a question?
Yeah.
Okay.
So. I was wondering which one M1 and M2 is.
Okay. The two bodies involved, they actually must exert the same force. So here's the Earth, and actually this is not the scale, right? The distance is much greater than this compared to the radius of the Sun. So if I drew this all to scale, the Sun would be much smaller and the Earth would be a tiny little dot. Okay, so the Sun exerts a force on the Earth, and what is the magnitude of the force that the Earth exerts on the Sun?
Equal and opposite.
Equal and opposite. It's a reaction, equal and opposite. So it doesn't matter which body you're talking about. Whoops, it's the same. It's the same force, just exerted in the opposite direction. But because the mass of the Sun is so much greater than the mass of the Earth, it doesn't appear to move very much. And in fact, the way we can account for this is to consider the center of mass. If I come to this and I look, where is the center? If that's the center of the Sun, where is the center of mass of the Earth-Sun system?
Very close, isn't it?
Yeah, it's
Right next to it.
yeah. If I could even get it right, that's probably too much right there. Right? It's the center of mass. Remember, and the center of mass is what stays stationary. The two bodies are going to move around the center of mass, but the Sun is so close to the center of mass already that the wobble that is induced by the Earth moving around it is very tiny. But that is exactly how some of these new planets these exoplanets have been discovered. They look for the wobble of the star. So you've maybe read, I hope you've been reading about these new systems where they're discovering planets outside of the solar system. And they have to be pretty big. Most of the ones that they discovered early on were big, because they're looking for a wobble, and there's not much wobble there from a planet, so you have to have a pretty big planet to produce much of a wobble. That's not much. Then the other method is to look for when the planets come in front of the star and they block some of the light. That's another method which doesn't involve a wobble, so it's not really relevant to this. Okay. So the force is the same, equal and opposite in that case.
So for the second one where you said M2E squared?
Yes.
So be the larger mass?
Well, it's the same one. It's the same situation
Yeah,
there,
yeah.
right? They're both moving in uniform circular motion. The Sun, the radius of the Sun's orbit is very small, just a little circle like that. And the Earth goes through a circular motion like this, right? So in one case, it's going to be the mass of the Earth times the speed of the Earth squared over the radius of the Earth is going to be this constant g, which has to be determined. It's called the gravitational constant. And that's the radius of the Earth's orbit. Right? Not the radius of the Earth, but the radius of the orbit of the Earth around the Sun. Okay? But the same thing would hold for the Sun. The corresponding equation would hold for the Sun, except that the speed and the radius of the orbit are all much smaller. But I have to have that same relationship.
Yeah,
Okay.
it's all one thing to me.
Right. Okay, so now here's what I'm going to give you a preview of Rizzi is going to try to give you an explanation of how is it that this gravity works. Because we have this understanding of forces like springs and tension, normal force, friction, all involving contact of some kind between two bodies. And yet, here it is, I have a body that's not in contact, and yet something is able to establish a force which pulls on this one and actually pulls on the Earth as well. Right? Somehow there's this relationship between them which is established over a distance. Okay, so one of the difficulties that's established by Newton's approach and his fantastic success is that he's writing down this differential equation like what I was showing you here. This differential equation here at the end. Here's this differential equation. So this force is acting over a distance, but what's in between the two bodies? It's not taken into account. It's abstracted out. All that's between the two bodies is a distance. There is nothing accounted for in between these two bodies. So you might be tempted to say there is nothing between the two bodies, but that's not right. Right? What's between my hands? Air. Now, okay, hold your breath. I'm going to suck all the air out of the room. What's between my hands? Space, all right? Okay, space, but what is space?
Space can only be defined as like a distance between two things, because if those two things weren't there, then space wouldn't exist.
That's what the Newton's way of looking at things. You can be lured into thinking about that if you're understanding Newton's equations and doing it through this Newtonian mechanics, because there's nothing in there. Space is just providing a place for things to be in this way of looking at it, and nothing else. Okay? That might lead you to think that space is nothing. That there's no massive bodies around, we've gotten rid of the air, and there's nothing else, so space is nothing. But this is not nothing. There's not nothing. Now there's nothing between my hands, right? Now there's nothing. But this is not nothing. At least it has quantity. Whatever it is has quantity. But it has to be a quantity of something, because quantity is a property. It's not a substance. Quantity itself, remember, is category of property is the first property of changeable things. Quantity is a property of something. So now space would be okay, except that space tends to invoke in people's minds the idea of nothing. Right? So space is not a good word to describe this. Rizzi wants to try to focus on the fact that there's something between here. It's a substance. It doesn't have mass, so it's a massless substance, but it's the stuff between massive bodies. It's the stuff between the Earth and the Sun, and between us, and between things here. Very simple thing, but it does stuff. For example, gravity goes through that stuff. Right? The gravity goes from the Earth to this object through whatever that stuff is. Okay? Also, electric fields, magnetic fields, light, all kinds of stuff goes through this stuff. And it has measurable properties. So it has properties, which is a substance. So Rizzi's going to give it a name based on this idea that it receives things, that it receives gravity, it receives electric field, it receives the light that goes through it. So it's acting in a way as to be a receiver, passing along something that it receives from somewhere else. So he calls it plana, which means field in Latin. So that's all it is, very simple. So the idea then is that gravity acts in the following way, and you'll understand this as you begin to read this book. Here's some massive body surrounded by this stuff, this plana. And maybe it's better to, I don't know how to draw it. I have no idea how to draw it. Okay, but it's the stuff.